These data sets that you see, it was the same data set that we plotted. I'll show you the plot very soon. It was the same thing. It was the same thing. It was the same thing. And if you can notice, the one that we plotted, we only use these DMUs. Okay. We only use DMUs A, B, C, the first three. That's what we used. Okay. That was the one. That was the one that we used. So A, B, C, but I've added D and E. And I have a good reason for adding D and E. So that is why I told you to type it into your Excel. All right, all of you have confirmed that you've typed it. Now I want to see which of you have tried to plot this. Which of you tried to plot it? Scatter plot it. Is there any of you who tried to scatter plot this data set? No? Nobody? Okay. But of course, you can scatter plot it, can't you?
Yes, Doc.
Perfect.
Yes, Doc.
So I'm not going to show you how to scatter plot it. And you can draw if you look at the D and E, watch it carefully. Watch the data set. I'm going to show you something very soon. Put these numbers in your mind, okay? The D and E. For the X1, you have 1.5 and then 3. For the E, you have 2.5 and 2.5. And then when you go to their second period, for the D, okay, you have 2 and 2, and then you have 3 and 2.5. Keep these numbers in your mind. I want to show you something. Okay. I want to show you something very, very important. Something very, very important. So I'm just going to switch and show you something on this video. Do you see the graph, please?
Yes, please.
Okay. Now, for the D, do you remember the coordinates for the X1 and X2?
D is 1.5 and
1.5 and
3 and 3, please.
1.5 and what? 3.
Yes, please.
So you can see that this is 1.5. They will meet somewhere here. They will meet somewhere here. Okay, this is 1.5 and that is 3. So they will meet somewhere there, okay, where my star is. Do you get what I mean?
Yes, please.
So if you look at where they are meeting, would it be efficient or inefficient? In the year 1, would it be efficient or inefficient? 1.5 and 3.
Doc, this will be inefficient.
It will be inefficient. Okay. Now, that same D, we go to the second year, it was 2 and 2. Do you remember?
Yeah.
It was 2 and 2.
Yes,
Okay,
Doc.
so this is 2. Okay. And then that is 2. So if you look at it, it appears that it would then be on the frontier. Okay, for D for dog. Okay, it will still be on the frontier. So it will be inefficient in year 1. But when it comes to year 2, that firm will be what? Efficient, D. And it will be part of the frontier. It will be part of the frontier. I want you to keep this point in mind because of something we'll calculate. A very powerful concept we'll calculate called the concept of innovators. Okay. So just remember, I'm saying that you should remember where they will be because I didn't plot them here. But you got to have it in mind that we have superimposed them on this data set. All right, now let's go to E. E for echo. E. What was the coordinates in year 1?
2.5 and 2.5.
Good. So this is 2.5 for the X1 here, and 2.5 will be somewhere there. Okay. So if you look at where my star value is, would it be efficient or inefficient? Would it be efficient? To be inefficient. Very good. Okay, so don't forget, okay, to be inefficient somewhere here. Now, what about in year 2 for E? What are the coordinates?
No, 3 and 2.5.
Good. So you have 3 here, you have 2.5 there. Okay. So if you look at E in year 2, would it be efficient or inefficient?
To be inefficient as well.
To be inefficient as well. Keep all of this in mind. Keep all of this in mind. All right. Now, the Malmquist Productivity Index that we calculated for the input-oriented efficiency score, which is what you see here. We indicated that in the input-oriented efficiency score, a lower value, a value lower than 1 is progress. And a value less than 1, a value lower than 1 is progress. A value greater than 1 is regress. And so we were able to establish that, but we indicated that you can take the reciprocal of the answers and then get everything in the right definition, because it doesn't sound well when something is less than 1 and you say it is progress. Okay, and when something is greater than 1 and it's regress. So when you take the reciprocal, you are able to do it. But we indicated also that in the mass DA software, the software does all of that for you. So there's no problem. Do you remember that?
Yes, please.
This was a formula that we had for the Malmquist. This was for FMC. And looking at the value, okay, if you take the reciprocal, we're able to realize that you will get 1.162, okay, which shows this is how we defined it. Okay. We're able to do the same thing for A. This is a Malmquist for A, which was stagnation, for B, which was progress, for C, which was also progress. We did this. I'm sure you all remember this.
Yes, please.
Do you remember that?
Yes, please.
Yes, please.
All right. So we're able to calculate the decomposition. And this was the decomposition we did. We were able to split it into this. We're able to know that for FMC, the majority of the productivity growth was coming from technical change. Okay, as you can see here, technical change in the input oriented was smaller. Okay, so the reciprocal will be bigger. And it was coming from technical change. And so majority was driven mainly by technological progress. All right. Now we are going to, this is where we are going to start today. And I want you to please pay attention to this. We are going to start today. We are going to run everything in our software. Okay, we are going to run everything in our software. And then we'll also run, in our software, we use 2 packages. The first package, we are going to use benchmarking to run the analysis, to see the results, to see the decomposition, to see the details of everything that we want to do. We're going to do that. Then we'll also do the same thing using fear, another package called fear. We're going to do all of that using that same data set. So by now, I'm expecting that you have your data set typed in Excel ready, just as I told you to do, because that is where we'll begin. Then if you have your laptop beside you, you are going to open the R, but don't open the R yet. Okay, so before we do the software analysis, I want you to understand some key terminologies first. I want you to know that in the our software we are going to use, there are some words you are going to see, and you want to appreciate it first. For example, there is a difference between output orientation and input orientation. Keep note. The OO is output orientation, the IO is input orientation, okay? And always remember that the numerator will swap with the denominator when it comes to output and input orientation. So if it is an output orientation, okay, the numerator will come down, the denominator will go up for the input orientation. So it's always a swap. Keep that in mind. Second, the word V that you're going to see in the R software stands for VRS. And the word or the letter C is going to stand for constant returns to scale. Are you following? Okay.
Yes, please.
So when you see V11, what does that mean? This is how I'll interpret it, but I want you to understand it. Okay, it talks about own period output-oriented efficiency of DMU in year 1 relative to frontier 1. Now watch word carefully. The way we used to define it in the slides, in our lecture notes, is slightly different from this. We will normally pick the one in the bracket, and then the frontier is rather outside the bracket. Okay, so it's like we go to the second one before the frontier becomes what is in the first one. But here, the frontier is the second one. So the efficiency of a firm in year 1 relative to frontier 1 is 1, 1. But if you look at 1, 2, 1, 2, look at 1, 2. 1, 2 means efficiency of a firm in year 1 relative to frontier 2. So year 1 relative to frontier 2. Okay, V21 is year 2 relative to frontier 1. Year 2 relative to frontier 1. And V22 is year 2 relative to frontier 2. Okay, so the number that comes first is the year, the efficiency score, okay, of the DMU. And then the second number is the frontier and the time period, the frontier time period. Okay, do you understand? And I hope you do.
Yes, please.
Now, the next thing is that if it is C, so all the letters V could be changed to C. It would simply mean that we are dealing with constant returns to scale. So please understand that if you see C11, C12, C21, C22, this simply means we have changed from the variable return to scale to constant. I want you to understand that. Now let's decompose the Malmquist. Do you remember that we decompose the Malmquist into efficiency change and the technological change? Do you remember?
Yes, please.
And the technological change, we also referenced it as technical change. It's the same thing. Technological change, technical change, all the same. Now, have that in mind and then watch this. This is the decomposition. I'm using those terminologies that we use, the C and then the V and then those ones. So this definition, the 1992, this was the original Malmquist. This was a decomposition. And please watch it carefully. The C here means that we are estimating everything relative to which frontier? Which frontier? The C means we are estimating everything relative to the CRS frontier. Okay, CRS frontier. A constant returns to scale Malmquist was developed by Fair, Groskopf, Lindgren, and Roos. And you can see that in this very definition, everything being estimated here was estimated relative to the CRS frontier. Now, the 2 means efficiency of a firm in year 2 relative to frontier 2. The C11 here means efficiency of a firm in year 1 relative to the constant returns to scale frontier 1. The one in the square bracket, Okay, the first part, the numerator, okay, is efficiency of a firm in year 2 relative to the CRS frontier 1. And the one below it is efficiency of a firm in year 2 relative to the CRS frontier 2. So you got to understand that with this definition, everything was estimated in relation to the constant returns to scale frontier. And these are the 2 decompositions. We know this. We know this. And this is what gives us. Now, this is the 3-part decomposition that they suggested. And this was actually suggested by Groskov, Norris, and Zahn in 1994. Okay. Now, they decided to bring the scale into the picture. That's what they did. They brought the scale into the picture. And so, as you know, in a normal efficiency, you can split the technical efficiency into pure technical and scale efficiency. So the same thing here, pure efficiency change and then scale efficiency change. And this is new. So that's why I want you to pay attention. Okay? And of course, the technical change still stands as it is. So look at the technical change part, the technological change part. Okay? If you look at it well, okay, and then you compare it with the same technical change part here, it is untouchable. It's the same thing. It has not changed. The same thing as the Fair, Groskov, Lindgren, and Rules one is the same thing. The only thing is this one here, the C22 over C11. That one is what has been split. And it's been split in a very interesting way. And I'll tell you why it's very interesting. Because that's the same thing here. So this whole thing means that you are estimating some of the things by VRS, and you're also estimating some of them by CRS. Okay. So the pure efficiency change is when you have estimated the scores relative to only the VRS frontier. That's why you see the same thing, V22 over V11. But watch this one. Watch this one carefully. Watch. You see that you have C22 over C11. But if you look at it very carefully, the C22 is over V22 again, and then the C22 is over V11. That is the scale efficiency. So the scale, you will always see the constant returns and the variable returns mixing together. I want to share something with you, very important here. Okay. Something very, very important, and I want you to pay attention. If you look at what is down here, okay, V22 over, I'm rewriting them here. Oh, let me take a different color. This is V22, okay, over V11. Okay, I'm rewriting. And then this one here, which is a scale efficiency, I want to show you something there. Okay, so it is times C22 over V22, if you can see it. Okay, all divided by, do you see it's all divided by? Okay, all divided by.
Yes, Doc.
Divided by C11. And now I want to make it times. So it's divided by C11. So I want to make it times, but I will not do that. In algebra, you have to swap the denominator and the numerator. So I'll just rather make it times V11 over C11. Okay. Now watch what happens. If you look at what is happening here, this whole thing is a pure efficiency change and then scale efficiency change. Okay. The pure efficiency change is this part here, the first part. The scale efficiency change is the second part. But watch it that we can cancel it and come back to the original one, C22 over C11. How? We can cancel this and this, all right? And then we can also cancel this and that. And then we'll be left with C22 here over C11. Are you guys?
Yes, Doc.
So that is what is helping you to know that it was actually a decomposition. It's like factorization and expansion. Okay. So here in the bottom, the tripartite, the 3-part decomposition here, it has been more or less expanded. It's been more or less expanded. Okay. Whereas in the original one, it's been factorized, more or less. And that is the 3-part decomposition. Okay. Take note of that. That is a three-part decomposition. And I want to share something with you. This decomposition, some people challenged it. Some of you are going to do this. That's what I'm teaching you. This decomposition, some other authors challenged it. What was the challenge? Well, Ray and Desley. Okay, let me see what I can show you. This is the one. Ray and Desley said that this decomposition we just looked at here has a problem. The problem is very simple. Why will you estimate some of the efficiency scores relative to VRS and estimate some of the efficiency scores relative to CRS? It doesn't make sense. Because if the technology is in the industry, the technology must be in the industry at one time. Okay, we cannot have VRS and CRS technology operating in an industry at the same time. Do you guys understand what I mean?
Yes, please.
Say that the industry is exhibiting VRS, and at the same time, that same industry is exhibiting CRS. So Ray and Desley, his paper was a very unique paper. It was published in American Economic Review in 1997. And he came, remember, this was about 3 years later after these people have postulated their model. And then he came and then redecomposed the Malmquist. And watch his decomposition. Watch it very carefully. Now, the Fair, Groskopf, Norris, and Zhang one, you have pure efficiency change, pure scale efficiency change, and then technical change. But Desley one, you have pure efficiency change. That one doesn't change. You can see that was still here. Okay, V22 over V11 is the same thing here. V22 over V11. Okay, so that one doesn't change. What about the one in the square bracket? Okay, watch it here. C21, C22, C11, C1. Now watch that one here. That one has changed. Okay. And you can see that in his decomposition, they do all by which technology? Well, if you look at it carefully, it appears that they were doing a lot by VRS technology until the ones in the bracket here, they do it by CRS technology. So you can see the decomposition, they still bring the one in the curly bracket, which was relative to constant returns to scale here. Okay, they did not use C throughout, rather use V throughout, and they called it pure technical change. Pure technical change, not just technical change, but pure technical change. And then they created a new scale efficiency. Now, if you can remember this scale efficiency here, okay, they created a new scale efficiency here and then took a square root of that as well. Okay. Majority of people don't use this because it's a little bit complex. Okay. Because even though he said that you can't do all by that, okay, they still bring both constant and variable returns to scale into their scale decomposition. Well, they said that is true. You should bring it rather into the scale decomposition. Watch it here. Okay. You should bring it rather into the scale decomposition. Everything else, okay, everything else came. But if you look at this definition, there was a constant returns to scale section here, and there was a variable returns to scale section here. But if you look at the Ray decomposition, those ones were all V. But the only thing was the scale. It was only the scale that had V and C all attached to it. So this is just to tell you that there is another decomposition, which is by Ray and Desley. The final decomposition. I'm telling you this, and many people don't learn this. Okay. And one of you can later on even write a paper where you compare all the decompositions of the Malmquist productivity index. One of you can just write a paper and then compare all the available decompositions. It will be a nice paper. Just the same data, run it on different decompositions. Now, the last one is by Sema and Wilson, and then Wheelock and Wilson. It's the same guys, more or less. Okay. And they came with a 4-part decomposition, not 3, 4. Now, watch, it's not different from the others significantly. The first part, which is the pure efficiency change, still remains by V22 over V11. The pure technical change was the same one that we saw in the Ray and Desley one. Pure technical change. If you check carefully, this is the same thing. Pure technical change. The scale efficiency change is the same one we saw in the Fair, Groskopf, Norris, and Zahn, FJNZ. Okay, it's the same thing here. Watch it. Watch it. Scale efficiency change. It's the same thing here. Okay, so they are kind of bringing all of them to. So that is it. And then finally, they added a final one. Very beautiful thing. They added a final one, which is the scale technical change. Scale technical change. Now, if you look at their scale technical change, that is the only thing that is different from that of the rest. And, however, if you look at their scale technical change, it is more or less like the scale change. It's more or less like the scale efficiency change of the Ray and Dessiny. Look at it here. It has one part there times another one part there. Okay. It has one part there times another one part there. But there's a slight difference. Okay. Sorry, there's even no slight difference in there. No, there's a slight difference. And here is a slight difference. If you look at it, it is C21 over vein 21. That's the same thing here. C21 over vein 21. But the denominator, you have C12 over vein 12. And here you have C22 over vein 22. But then the C12 over vein 12 is rather on this side. But this is just to show you that there are multiple decompositions of them. Nobody have I seen really using this Summer and Wilson one. I would suggest that in one paper you want to do, and I can do all of this at a go for you. You can just do a beautiful paper and compare the different. You see similarities and differences, and you can come out with, which one you think makes practical sense. This last term, okay, is the product. This last term is a product of the fair Groskopf Lengren and Roos efficiency change, okay, and then the pure technical change. Okay. Whilst the scale change here is a product of the scale efficiency change and another one they call scale, or what they call it, change in scale technology. That's what you have here. Scale technology change. Okay. Change in scale technology. It's a very confusing one, but like I said, so there are 3 different decompositions of the original Malmquist. Right. So now we are ready to do the Malmquist in the